Hi everybody, this is John Fellenstein, Professor Polymer from the Akron Global Polymer Academy at the University of Akron. Today we're talking about polymer chains and cross-linking. So the material that we're going to discuss today are polymers, and the plastics in our lives are polymers, but that's not all. Everywhere we look, we can identify these materials. But what exactly is a polymer? Here is a demonstration. Can you predict what will happen when I pull this string of beads out of the cup? Ready? Go. That was pretty cool, wasn't it? The long chain of beads is a polymer molecule. Scientists use molecules to understand things that might be too small or even too far away to see. Models help us get a deeper understanding of objects and ideas. That chain was long, wasn't it? Well, do you think you can estimate the total number of beads that were in that chain? I'll give you a hint. It's more than 100 and less than 1,000,000. What would be the best way to figure out the total number of beads? Here's something you could do. You could just take a random guess, or you could count every single bead in the chain. But if you're like me, you'd lose your count and you'd have to start over. 1, 2, skip a few. But if I told you that each section of the chain was about the same length with the same number of beads, and we knew how many sections of bead there were, or how many sections of chain, then we could do some mental math. So here it is. This is a mental math problem for you. There are about 100 beads in each different colored section, and there are 15 sections of chain. So how many beads are in the entire chain? So if you said about 1,500 beads, you were correct. So here we have this polymer model, but we need a little more information. Each individual bead is what we call a repeating unit or a monomer. These monomers connect in long chains to form polymers. One bead is a monomer, and the entire chain is a polymer. Here is an example of a polymer model using plastic chain links. Notice they're all the same, and I can remove one. This individual link is a monomer, and when they're all connected together, we call that a polymer. Monomer. Mono means one, and mer means parts or pieces. Polymer. Poly means many, and mer, again, means parts or pieces. Here are a few ways you can make your own polymer models at home. You could start with strips of colored paper, and if we turn those into a loop, or the link of a chain, we can make our own polymer models in this way. Here's one that's a little bit longer. Alrighty. Another thing that you could do is you could connect paper clips together as well to form your polymer chain models. We can change the properties of some polymer materials by adding another substance. This is called cross-linking. The added material causes the polymer molecules to grab onto each other, changing the way that it behaves. Here is an example of a cross-linked polymer using plastic links. So notice the purple links are the polymer molecules, and the yellow links are the cross-linkers. Alrighty, so it changes the behavior, it changes the structure of the material. Here's another example using paper clips. So we have the yellow polymer molecule chains that are all connected together, and then the purple are the cross-linking materials there. I really like this demonstration because it's very, very visual. So here's my polymer molecule. Now in this case, it is a small metal bead chain, like the ones that some of you have in your closet to turn on the light in the closet. And I have two of those. And notice that they can behave independently of themselves, right? But if I start to introduce something into that system, this is a small, very strong magnet, and I can connect the two chains together with the magnet. So we're going to try to do that here, so you can see what happens. Usually this works better when I have a volunteer to help me with the magnets, but that's okay, no volunteers today. Almost done. Okay, so now the two chains are connected with the magnets. They cannot function independently, right? We call this cross-linking. They have a tendency to get all jumbled up and tangled together and look like this. Now that's only two of the chains. But if we have a whole bunch of them, say 20 or 25, and a whole bunch of magnets, then it looks like this. Pretty cool. Here is a fun cross-linking demonstration. This material is a two-part polyurethane foam. So you mix equal parts together and we have a cross-linked chemical polymer that results. Okay, so I've already added the first part with some food coloring in this little cup. Now I'm going to add the second part. It takes a few minutes for this to happen, so we will talk about cross-linking a little bit more. Here we go, we're going to add the second part. We have to stir it up very, very, very well. Alrighty, we'll let that sit right there for now. Hopefully you can see it. So we've been talking a little bit in other videos about chemical reactions and things that you can see as an evidence of a chemical reaction. In this case, one of the things that we will look for is something that's producing a gas. So I'm thinking that this red substance is actually producing a gas, and that is the proof that there is a chemical reaction taking place. So here you have it, the finished product. Still a little bit tacky, but it should solidify a little bit better. So this material will expand to about 30 times its original volume. That is a cross-linked polyurethane foam. It got warm as well. So there's another type of thing that we can talk about, exothermic reactions. We have one more cross-linking demonstration, and let me get that ready for you right now. These are two products that you can buy at the grocery store, or you can get them online as well, that you can use to cross-link a polymer. The Elmer's glue is the polymer, polyvinyl alcohol, and the borax, sodium tetraborate, is the cross-linking solution. So in the white cup, I have some of the Elmer's glue. It's yellow because I just added food coloring to it. And in this cup, I have some of the borax solution. So I dissolved it in water to make it easier to mix. We're just going to add a little bit of that to our glue. And we're going to stir it up. You can use our finger to stir it. And notice what happens. Ooh, we'll stir a little bit more. So here we are. We're not really making slime, we are cross-linking a polymer. All right, so the more we work it, the more stretchy it's going to be. Cross-linked polymer putty, not slime, CLPP is what we call it. I need a little bit more. We're going to mix it up in our hands. Now this is what we call a non-Newtonian fluid. Okay, so it doesn't behave as normal fluids do. Under certain conditions, it acts more like a solid than a fluid. Right? And this material has what we call strain rate dependence. And what that means is that the amount of strain is it will change according to the amount of strain that you put on it. So it's the rate. So if I'm straining it at a very slow rate, it's going to stretch and flow like a fluid. However, if I increase that rate of strain, it's going to change the way that it changes. So if I pull it quickly, it's going to break, and it acts more like a solid than a liquid. Cross-linked polymer putty, fun stuff. Keep it off of your clothes, keep it off of the furniture, keep it off your pets, keep it off your carpets, and don't do this. Okay, because you don't want to do that. Only I can do that. Have a great day, everybody. Stay safe out there, and go Zips.